You know, right now, all around you, and even inside of you, there's this secret dance happening. It's this constant, completely invisible movement of molecules. Today, we're going to pull back the curtain on the science that lets us not just see this dance, but actually understand its language.
So let's start with a little thought experiment. Imagine you're a detective. You find this tiny unknown residue at a crime scene. It's way too small to see clearly, and you definitely can't taste or touch it. It could be anything. So how in the world do you figure out what it is? This is the exact mystery we're going to solve today.
Well, the answer lies in this really fundamental truth of chemistry. You see, just like every person has a unique fingerprint, every single type of molecule has its own secret signature, a one-of-a-kind identifier that sets it apart from all the others. And our job right now is to learn how to read it. So what is this molecular fingerprint? It's pure motion. See, down at the atomic level, nothing is ever truly still. The atoms that make up a molecule, they're locked in this perpetual natural dance. They're constantly wiggling and stretching and bending, and scientists have a name for this: molecular vibration. Okay, to really get this, we kind of have to update our mental picture. Forget about those rigid ball and stick models you might remember from science class. Instead, I want you to picture the bonds holding those atoms together, not as stiff little rods, but as flexible, bouncy springs. Trust me, this simple little shift in thinking changes everything. Now, with those springs in your mind, you can almost feel the movement, right? This dance has two main moves. First, you've got stretching. That's where the atoms pull apart and then snap back together, almost like they're breathing in and out. Then there's bending, where the angle between the atoms changes. They can wag or twist or even do this little scissoring motion back and forth. And this is where it gets really, really cool. A molecule, especially a complicated one, isn't just doing one of these things at a time. Oh no, it's stretching, bending, and twisting in a whole bunch of different ways all at once. A simple water molecule has three main vibrations, but a more complex one, it can have dozens, maybe even hundreds of these distinct movements happening at the same time. It's not just a dance move, it's a whole symphony of motion, and every single molecule has its own completely unique symphony. Okay, so great concept, right? Molecules are always dancing this incredibly complex and unique dance. But let's be real, these things are unimaginably small. So how on earth can we possibly see it? What kind of tool could we possibly use to peek into this invisible world? Well, the tool that makes this all possible is called vibrational spectroscopy. Specifically, we're talking about infrared or IR spectroscopy. The best way to think of it is like a special camera, one that doesn't see color or shape, but instead sees the energy of that molecular dance. It uses infrared light to basically translate the rhythm of those vibrations into something we can actually read. So, how does it work? It's actually a pretty logical four-step process. First, we shine a beam of infrared light straight through our sample. This light, it has a whole range of frequencies in it. Step 2, the molecules in the sample will only absorb the exact frequencies that match their own natural vibrations. It's kind of like they're tuning into their favorite radio station and ignoring all the others. Step 3, when they absorb that energy, their vibrations get bigger, the amplitude increases, the dance doesn't change, it just gets more energetic. And finally, step 4, a detector on the other side measures which frequencies made it through and which ones got absorbed. That resulting pattern, that is the fingerprint we've been looking for. And this is what that fingerprint actually looks like. The machine spits out a graph called an absorption spectrum. Every dip in that line represents a specific frequency of light that the molecule soaked up. In other words, a specific dance move. And altogether, these peaks and these valleys create this beautiful visual map of the molecule's unique vibrational symphony. This right here is the absolute heart of the whole technique. The most important thing to remember is this. Just like a human fingerprint, no two different molecular compounds will ever produce the exact same infrared spectrum. An alcohol molecule is going to look totally different from a sugar molecule, which will be completely different from a plastic molecule. It is a positive ID every single time. And that brings us right back to our detective story. By taking that unknown residue, running it through an IR spectrometer, and getting its absorption spectrum, we can then compare that fingerprint to a huge library of known fingerprints. And when we find a match, boom, we know exactly what our mystery substance is, mystery solved. And this incredible technique isn't just for TV detectives, you know? It is a workhorse of modern science that affects our lives every single day. It's used in forensics to identify drugs, it's used in pharmaceuticals to make sure the medicine you take is pure, and it's used in countless research labs to develop the new materials of the future.
So we've figured out that every single molecule is performing this constant, unique, and totally invisible dance. And through the genius of spectroscopy, we found a way to watch it. It really makes you wonder, if we can learn a molecule's entire identity just by observing its dance, what other secrets is the universe just waiting to tell us if we can just figure out how to look?